Shall we begin? The talk today is on software. Software got its name because hardware you could lay your hands on. Software were the programs which told the machine what to do, and they were somewhat soft. They got that name as contrast with the hardware which you could lay your hands on, because in the early days of machines, people didn't really understand machines. Software is what tells the machine what you want done. That's the sum total of it. Now, in the early days with the hand calculators, you turned the crank and you threw the carriage over and so on, and you controlled it by your hands. And the early IBM machines, there were plug boards. You put wires from the columns in the cards to where you wanted in the machine, from where the answer were in the machine to where you want punched on the card or where you want to print it. We wired up single boards, and in an accounting room, for example, each operation would have a board. It would be stored away, so each week when you went through the accounting process, you picked up the same boards. You didn't rewire them because they were rather troublesome to wire, to say the least. Now, after George Sibbes's first machine, he used paper tape. And paper tapes are a terrible thing to use. You can't make insertions very well. When you glue the tapes together, the glue gets stuck in the fingers of the readers. It's troublesome. But you won't see much anymore. The ENIAC in 45-46 was the first electronic machine. And it was designed to do integration of ordinary differential equations for trajectories, to build bombing tables or ballistic tables. Well, that was the design. And so it was designed pretty much like a glorified IBM plug board, except the machine was in a room about this big, and the cables went all the way around on trails around the room. However, actually the first problem run was part of the original studies of how to build hydrogen bombs. So the machine was used differently. And in fact, the way they wired it was so awkward that ultimately Metropolis and a guy named Dick Clippinger devised a method of wiring the machine once and for all, so you then program from the ballistic tables, and so you merely set numbers, and that would be the program instead of rewiring it all the time. Now, real internal programming became a reality when we had registers. We began with machines with 2 and 3 registers. We got up to 10 or 12 or 15. That was a lot. Well, you can't do internally programming then. I am inclined to believe people thought about it. When we got enough internal programming space so we could really write out programs, it was began to discuss it, as had Babbage. Now it happens that von Neumann was hired as a consultant, and he wrote up the reports on how to program. And so it's attributed to him, but Harry Huskey has written that they had discussed internal programming long before von Neumann ever was a consultant. Watching around, von Neumann never either claimed that he had done internal programming or denied it. So, since he's dead, you're left. But my inclination is the attributing internal programming to von Neumann is probably very dubious. Now, in the early programming, when you programmed absolute addresses, if there were an error here, you want to put something in, you took that instruction, replace it with a transfer, put that one over to the transfer place, put down the additions, and transfer it back again. Now, when you found another error over here, you did the same thing. And pretty soon the control was like a can of spaghetti all over the memory in very strange ways. And it became very, very hard. And we lived with it for a long while. Now, we very rarely got the idea of reusable programs. Even Babbage had the idea. We called them libraries in those days. We write out a square routine, we put it in the machine, and we reuse it. Everybody wants it to use the same one. And we put them in definite locations at first. But if the square routine is in that location and the sign is in that location and so on, you have got to program around all those parts. And pretty soon the library is so big that it all can't fit in the machine at once. So we turned to relocatable software, which was in the von Neumann reports. The von Neumann reports were Army reports. They were never published officially. They were just issued. And everybody had a copy, but they were never really refereed and published. The first published software book was on the EDSAC out of Cambridge. I told you, I think, that in 1946, Mach and Eckert held an open session and told everybody everything they knew about how to build computers. And Wilkes Maurice Wilkes of Cambridge was there. He attended the thing, went home, and he built a machine and got it going before anybody else did. So his was the first machine, and his book, which we'll talk about several times, was the first programming book. Now, pretty soon, somebody had an idea that I could write a program which would take the letters ADD at read time, when I was reading in a machine, and convert it to the pattern of zeros and ones, which was the crazy instruction the designers had built. And so we had symbolic addresses, symbolic names converted. And then somebody said, well, we could do the same with addresses. I could call the address A, and you could let the machine assign that, and the machine will remember where A is, and every time we refer to A, it will give the absolute addresses. Those were primitive assembly programs, and what you tend to call machine language, but that really is a fancy business already. Now, that went along for a while until a very much better one called SAP, Symbolic Assembly Program, was written, which really did its job fairly well. Now, we were using IBM 701. That was expensive. I calculated this morning coming in, we paid $300 an hour to rent it. Since there's been inflation 10 to 1, that's like something like $3,000 or more per hour, which is something like almost $1 per second. So you can see why we tended to economize on machine time and not worry about human time. At $1 a second is kind of expensive. Well, I spent 1 year with the aid of a lady who did most of the work, filling up 32,000 registers of the IBM 701 with a program. And at the end of the time, I said, I will never again ask any human being to do a job like that. It was just awful. She did it very, very well. I'm not complaining. But it was not fit human being living. I had heard about a symbolic system up at Poughkeepsie, so I said to her, next program, send up for that and get it. We sent up for it. They sent it down. It didn't run. Why? Nobody ever used it. Well, they helped us get it going. Now, at IBM headquarters, there were about 100 of us using the machine. About 50 IBMers, about 50 like the young lady and myself, who were from outside coming to use the machine. And they gave us office space nicely. And we all ate in the cafeteria most of the time, although every once in a while I'd go to lunch with the guys who were building Fortran, and we'd go out to a fancy restaurant. Well, we told these people, and there must have been 100 of them. Only one, so far as I never could determine, was interested in a symbolic system. All the rest of the programmers wanted to use the same old absolute binary program they'd always used. It was too wasteful machine time, they said. Well, programmers were very, very slow in adopting the better methods. When Fortran came by, which means formula translation, written by Backus and a bunch of his friends, they set out to do what people normally do, translate high school mathematics along with a few calculus words into the machine language. They wrote what I will say is a psychological language. They designed it to fit people. Now, when they started, people said it can't be done. If it can be done, it'll be so inefficient you can't afford it. And in any case, even if it could, nobody but sissies would ever use Fortran. A good man code would write square in machine language. Well, that's the way. Now, along about about 1958, ACM with a bunch of logicians got together and backed a language called Algol. I was involved in the sense that I was president of the ACM at the time and had to find the money to send Al Perlis to Europe to have a world conference on how to design a language. Well, they designed it. It was logically beautiful. It was written in logical language, a Boolean logic, which normal mortals can't read, and even they couldn't read sometimes. Well, it was supposed to be the great savior. Well, you know the situation. Fortran is still around, and you haven't seen the Algol program for years. Why? Because I say Fortran was designed psychologically, and Algol was designed logically. Those programmers who design logical languages don't get their language to last long. When you come around designing a language, don't let a logician design it. Look at the people who are going to use it, ask how they think, and design it psychologically to fit them. The tremendous survival of Fortran tells you the value of psychological design of language as against logical. Logical just isn't very good. Now, that was the beginning of a time when we had POL, problem-oriented language. We had a whole bunch of those for a while, one for doing this, that, the other thing. The trouble was, if you had a problem doing two of them, two different things, the program languages didn't blend together very well. So we gave up the idea of writing special languages for special areas of problems. We still do, to some extent, have business languages and scientific languages, as we had, but Ada, as you know, is an attempt to be a universal language. Now, Ada was designed by a bunch of programmers. And in my opinion, it suffers exactly that fault. It's a nice logical language, but it's not fit for human use. And it's not really going to work out too well. Now, I tried out an experiment. You know the government frequently sets us out contracts that shall be written in Ada. So I called some of my friends who were involved in running software houses and said, how's it going to work out? Will it work out that the programs are written in Fortran, debugged and got running, and then converted to Ada with all those mistakes? They said, yeah, about 90% of the time. And I suspect that's something like what is happening right now. Although the contract says you shall do it in Ada, it's very likely it'll be done in Fortran and then converted over with all those attendant mistakes. Now, in 1962, Lisp language began. McCarthy thought of a language designing for logical reasons. And it was improved and extended by various friends, logically, abstractly. A student one day said, hey, I could write an assembler in Lisp, language itself, and cause it, by and large, to assemble itself. McCarthy said, you could? He said, sure. So they did. It's one of the first examples of using a language to assemble itself. It's a very useful technique. Now, let me digress and talk about the 650 machine that I used. It was a 10 decimal digit machine with a drum. And so therefore it was a 2-address system instead of the typical 1-1. The first address told you where to find the number or put the number, and the second address told you where to find the next instruction. So you could carefully arrange it so the next, as the drum came up there, right as you're ready to read, that instruction was there. Rather than having to go all the way around to find the next one, you could place them just so they'd be right. And the machine would operate much faster. That, of course, also depended upon where the numbers were put. Whether you put them here, there, yon, it had to be right where you wanted it, when you wanted it, then it would run very fast. Otherwise, it would go round and round and do very little. So the problem, what we call minimum latency. How do you design a program to store here, there, yon, so it'll run as fast as you can make it? IBM produced a SOAP program, symbolic operating assembly program. They made 2 copies. They wrote out straight out, call them copies A and A. They loaded A in the machine, and they ran A through it to get an optimized SOAP. Then they loaded the optimized SOAP in and ran A through again, and observed how much faster the second pass than what the first was, so you knew how much SOAP did in improving things. Another example of a program which optimized itself. This business of using programs to do themselves has proved very popular and very, very effective, and you want to think about the recursive aspect of how you can make a lot of work be done by the work you're doing. It's a very powerful technique. Now, let me talk about that book from Cambridge, England. I reviewed the book. In Appendix D, there was a little program which had been written because the program man wanted to write could not fit into memory. So he wrote a little piece here and put a little translation there. It was an assembler. It wasn't called that, but that's what it was. When I reviewed it, I studied over for a long while and realized that's what it was. If they put an Appendix D, did they know? In the second edition, it was still an Appendix D. Did they know what they'd done? No. I'm raising the question, when is something known first? We tend to give credit to the first person who says something, but that really isn't right. There was a time when I and a bunch of other people in computing realized one day that computers really were not number crunching machines, they were symbol manipulating machines. We went out and gave talks. And I could watch the audience nodding their heads, oh yes, and I knew most of them did not understand what I was saying. They didn't understand they were not number crunchers, they were symbol manipulators. But that's the way it goes. Now you can say that originally Turing machine back in 1937 was and demonstrated symbol manipulation. That's what it was. And you can also claim, if you wish, that he must have understood an interpreter, because that's how he proved that every machine was equivalent to any other machine. The universal Turing machine was really any one of the machines with a suitable interpreter. So he must have known. But did he? The answer is no, probably not. Now history tends to be charitable and give the first guy credit. There's a saying, however, that says almost everybody who creates a field never understands it correctly. It applies certainly to physicists. Many physicists have created a field and then they have been a drag on it. Einstein started quantum mechanics going, but he never accepted quantum mechanics. He always opposed it. He didn't believe that God played with dice, as a famous saying of his was. Well, coming back to 650, having realized the machine was 10 decimal digit machine, and I wanted a floating point, and that was a fixed point machine, I would have to build an interpreter. So I hit upon the following idea. Of the 10 decimal digits, I would use 3 for A, 1 for the operation, 3 for B, and C. Take the number that's in location A, do this operation with B, like add, subtract, multiply, divide, and put the answer in C. I have four instructions, but of course, only 4 of those, add, subtract, multiply, divide, need both addresses. If I put a 0 in here, the machine would look here for further information, what instruction you wanted. So I had a whole bunch more instructions. Well, now I wrote this program in my mind. Start. You assign some register, the current address register. You go there to find out where the instruction you want to obey is. You go to that location, you get the instruction. You store the A, you store the B, you store the C. You take the operation, add a constant to it, transfer. Here you find a subroutine describing that operation. And here's a bunch of which were transfer instructions. When these were done, they transferred to here. You added 1 to the current address register. You went back to start after cleaning up. If it were a transfer instruction, you transferred to here. Now you see, I've not told you the language. I've told you how to build a language. All meaning is contained in what those subroutines are, correct? Everything is contained in here. What do those instructions mean are what you put there. You could write any language you want. Now that one is a language in which every instruction meant what it meant without any contingent about what went before or after. You could easily have arranged, I could have, that if this instruction obeyed, it sets a flag, and when this instruction goes by, it looks, oh, that flag was done, do this. If not, do that. I can make a language which depends upon context. I didn't. This was a context-free program. But you see how you do it. I want to dwell on this, how utterly simple it is to build an interpreter. Now, the difference between an interpreter and a compiler is very simple. An interpreter does it, and every time you come to the same instruction loop, you do the same translation. A compiler makes the translation once for all, writes out the translation, and then runs the problem. And there are subtle logical differences between the two. You've got to be careful. But fundamentally, that's the idea. And for machine efficiency, we usually make a compiler. But if you're going to do floating point, you have to really do this. I'm sorry, you have to do a compiler. You have to do an interpreter for floating point, because you don't know which numbers are going to be where, how much you have to shift back and forth. You can't really build a very good one. So sometimes you build interpreters, sometimes you build compilers, and now we build compilers on top of compilers and interpreters on top of compilers and so on. We do this all the time. This is how we make a machine look like what we want. And I think it should be clear to you, if you can define a language uniquely. Write out the subroutine, write out something like that, and you have now the machine behaving in this language. Now, one thing I did was interesting. The machine had 2,000 registers. I put all this in the upper 1,000. This machine, with these three addresses, could never refer to anything other than the lower 1,000 registers. There was no way your program could interfere with the stuff I had written. I had built-in safety. Protection against stupidities on your part was protected that simple method. Well, now, I say I understood the thing. I learned it from somebody else. I say they didn't understand it. That's that funny thing, and I want to say it's very common. Almost everybody in physics has done this. Now take myself. You know, I suppose, that I'm the father of error correcting codes. Well, some guy who knew me said to another friend, you know, I don't think Hamming ever understood error correcting codes. A friend of mine repeated to me over the phone. I was just about to say, why that? And I shut up and said, over the phone to him, I said, yes, he is probably right. The person who discovers something rarely understands it. They have their feet so far in the back and all the trouble they had, they don't see the light, whereas the people who come afterwards see it much more clearly than the person who did it. Perhaps the best illustration of this point, besides telling you my personal story, is Newton. It has been said Newton was the last of the ancients. He was not the first of the moderns. Almost all creative people, when they create something, do this. So the reason we're telling you is twofold. If somebody else has created a field and he says this is the way to do it, you're entitled to ignore him. On the other hand, when you create a field, remember to shut up. You don't really understand what you did. Now, I started that method with 4 rules: easy to learn, easy to use, easy to debug, and easy to use subroutines. Now, let's skip the 4th one because it's tied up with the crazy ideas we had about subroutines, which are of no use to you whatsoever. It would appear that I was doing top-down programming. Easy to learn, easy to use. That's where I'm going to start. The first thing I did was to write essentially this inner loop. I wrote it down in my notebook. In other words, I went from bottom up. I wrote the very bottom. Once I was convinced that this could be done rapidly enough, then I went to top-down again. So while I like top-down programming, I know that you have to do bottom-up also occasionally. There are a million methods of writing programs, and we'll talk about various times. Again, I want to point out the difference between logical and psychological language. This A operation B equals C was something, remember that said the number in A times one number in B is to be put in C. It was going to be programmed by a bunch of high school graduates to a great extent. They weren't logicians. Machines were not common. I wrote a language which was easy to understand, not only for them, but for a second reason. I understood the problem by that time of what it really was. Machines were not widely known. They were being used in physics. But if you don't know what machines can do and can't program, you don't know what kind of questions to ask. And so the problems coming in were all problems of what they would have done if there had been no machines, except they could do it faster. My problem was to get a language so easy that the physicists and chemists and engineers could not refuse to learn it. Once learned it, they would know how to ask the appropriate questions. That was a problem I really grappled with. How to make a language so easy that PhDs in physics can understand it, not programmers. Now, I understood a great many things about things that aren't usually discussed. I want to point out one feature, a language called APL. It was again devised by a logician, originally devised to describe circuits, but he developed it into a language. Now APL has its devotees and it has its people who can't stand it. The characteristic of APL is it's very, very terse. You can write one line of program and change a comma or something and the whole thing is different. Well, people who like it because it's very simple. You write it out and you write very, very little and you get a great deal for it. People don't like it because you make one mistake, you get something completely different. It has almost no redundancy. The language I'm talking to you now has about 60% redundancy, meaning you can drop about 60% and still make it out. It has to be this way. I'm talking at a rate you have to grab it on the fly over an acoustic channel. Now the written language is different. It's about 40% redundant. Because you can stop, you can backscan, the channel is not anywhere near as noisy. If you think the written and spoken languages are the same, try writing dialogue and see what happens to you. You can't write the language you speak. I know you think you can, but you can't. They're different languages. And when you do find a book with dialogue that sounds very good, it really is not how people speak. So we really have a couple different languages. And redundancy is necessary. If you write a very, very compact language with very low redundancy, it's not fit for human use. If you write one with very high redundancy, it takes too much time to write the stuff out. So you have to find your way between those two. Well, I was interested in the matter because I knew we were writing languages for machines. So I invited Professor Pei of Columbia, who is a very popular linguist, down to meet me at IBM headquarters at 590 Madison Avenue. And I would take him to lunch afterwards. So we showed him the machine, all the glamour. And we took him to lunch, and at dessert time I said, well, Professor Pei, we are regularly inventing new languages to work with the machine. It's a language between machine and humans. Human to machine, and later on maybe machine to human. What can you tell me about the engineering efficiency of language? He could not understand the question. He could tell me how some languages put plurals in the middle of words. He could tell me all kinds of things about all kinds of languages. But the thing I want to know is, how do I write an efficient language for communicating to a machine with enough redundancy? Why do we have the number of synonyms we do? Why do we have the antonyms? Why do we have irregular and regular verbs? Why? What are the values? Now, there is a presumption that the language we are using are reasonably well designed to do the job they're doing. Not certainly, but it's a reasonable presumption. Now, the language we use for is not what you think, and this may be out of place, but one of my favorite stories about my wife and myself when we were in New Jersey, our dining room table breakfast table was right next to some windows looking on the garden. We're having breakfast prior to me going to work, and she says, Dick, it's raining. I look at her and say, what's wrong with that dame? She must know that I can see it's raining. Then I say to myself, what did she really say? What she said was, I've had my second cup of coffee and I'm fit to talk to. Well, I spent much of that day at Bell Labs watching how much of what we say is not what it appears to be. And it's amazing. The enormous amount of what we say is literally not correct. No way. So the language does a great many other things than what you think. Our natural language has a great many other features which a language to a computer would not have to have. Well, we have not studied the problem. When I heard the Japanese were planning to write fifth generation computers, the speed was all right, but when they were going to use AI to do things, I thought they would not succeed, and they didn't, because they were not profoundly studying the nature of language. And until we do, we will get language like Ada, which are logically all right, but they don't fit the human animal to do the kind of things the human animal does with language. It's a very, very miserable thing. Now, I point out there are two languages. There is you to the machine, and the machine back to you. They need not be the same language. You want a terse one in, and you're willing to put up with a rather more verbose one coming out. Frequently what comes out is so terse you can't figure out what it means, and you're willing to settle for much more printout, but not too much. So it's a problem of designing languages that communicate ideas to machines, but unfortunately we don't know what ideas are, so we don't know how to do it. Now, I made a prediction at Los Alamos for them when I was there visiting once 2 weeks, that the 5th generation would in fact do what I told you the other time. The machine hardware fell right on the curve. The software was a total flop. They did not get anywhere using artificial intelligence to make programming easier. No way. We don't understand what we're trying to do. Now, you read continually about engineering software because software is a major problem for everybody. It sounds nice, but should I believe it? Let's consider some situations. When the Russians and the Americans wanted to get out in space, they did things pretty much the same way, all things considered, and allowing a little bit for espionage. But if I ask a couple of novelists to write on the greatness and misery of man, I claim I'll get 2 very different novels without telling you just how I'll measure them. If I give 2 programmers a complex problem to do, and they do it independently, I say I will get 2 very different programmers. 2 different programs. I will not get the same, or even close. My conclusion from that experiment is, and it's only an intellectual experiment, programming is closer to novel writing than it is to engineering, because the engineer is bound by a large number of hard laws of physics, and the programmer is much more bound by his mind. Any ingenious thing they can think up, just like a novelist. The novelist is bound by their imagination to a great extent. The programmer is bound by their imagination much more than they are bound by hard rules. Therefore, it's not so likely that you're going to be able to produce engineered software. It isn't the same problem. It's more like novel writing, as far as I can see. Now, there's lots of ways of improving productivity of programmers. There's lead programmers and top-down and bottom-up and this, that, and the other thing. I have only one method that I recommend extensively. It's called think before you write. Now, this is something you have great trouble doing. The teacher can preach in class of programming, think before you write. The students will rush out, sit down at the terminal, and start writing the program immediately. Now, I had a man working for me for a while. He would wander around the halls, just wandering around, twisting his hair now and this, and being sociable. And then after 3 or 4 days of wandering around doing nothing that was visible, he would sit down, write several thousand lines of code, have them debugged and going. He got far more done per week by not sitting down until everything was clear in his mind and writing it out then. And I have found the same thing. In fact, my recommendation to you is don't write 1 line of code until you've decided what your acceptance test will be. What test will you apply to your program to decide that it's running correctly? Not that it may be, but what's going to be your acceptance test? Because if you start looking at acceptance tests where all the trouble occurs, you will begin to decide you better write that program very straightforward and simple so it's easily tested. As a consequence, you'll get there much, much sooner. I promise you, almost always. Now, there are exceptions. Some problems, we don't know what the problem is, and so we start programming to find out what the problem is. And there are a lot of those. And I warn you about those. Take, for example, a Nike project. We acquired a contract at the request for the Defense Department to build a guided missile. The contract didn't specify very much. As we found out what we could do, we could then fill out the details of the contract. We didn't know at the beginning what was reasonable ranges or anything. Your idea that you want to write a definite contract for somebody to do something is not really a good way to work on open-ended problems, which you don't know what you're doing. You get very bad results. Sometimes programming is a means for finding out what you're trying to do. Now, that usually means when you do that is, after having found out what more or less you're doing, you throw away the whole thing. Now you understand the problem, you reprogram from scratch, and you're better off. But I cannot recommend it too highly. Think before you do any programming, and particularly settle with yourself, how will you decide what you're going to do to accept that the program is running right? It's a very, very powerful thing to do. Now, I saw a bunch of ones the other day, numbers, about the improvement of assembler over machine language is said to be 2 to 1. C language over assembler was 3 to 1. Time to batch was 1.5 to 1. Unix monitor to monitor was 1.5. System quality assurance versus debugging was 2 to 1. Prototyping top-down was not so much. C++ was almost 2 to 1 over C, and reuse was something 1.5 to 1. The total worked out to be approximately 90. Let's say it's 100 for sake. Programming from when we started has improved by a factor of 100, meaning working reasonable time. In about 4 months, what we would do, you could now do in 1 day. There'd be about 400 working days and about 100 working days in 4 months, right? So that's all we've done. Computers have moved from either 1 operation per second, or if you want 1 per 20 seconds, up to 1 billion, 10 to the 9th. You've only got 100. The situation is really pretty bad. It's pretty bad indeed. The machines have enormously increased, and you furthermore believe that parallel machines are further going to increase, but parallel machines are going to put a bigger burden on programming. We desperately need better programming. So we ask ourselves, can we teach programming? Well, let's first look at a few other facts and come down to that. One fact is that programmers differ in productivity more than 10 to 1. In fact, my friends who form software houses, I've said, look, pay your good programmers anything and fire the bad ones. Now, you may not get away with firing them, so what you do is you hire them on contract. And you pay the guys who deliver on time big sums of money, and those who don't, you don't rehire them. If programmers are more than 10 to 1, there are times when you could afford to pay the bad programmer to stay home and not come to work, and you'll be ahead. I'm serious. Well, now we come down to, can we teach programming? Well, I liken programming to writing novels. I point out to you the following facts about writing. Almost everybody who takes a course in creative writing does not become a great writer. Most of the great writers in the past did not take courses in creative writing. Can we teach good writing? Yes and no. It's evident that we don't do as good a job as we'd like to. If you want to become a great novelist, the way is not to start taking creative writing courses. That isn't the way to do it. Does experience help? The more years you're programming, are you better? Let me ask you the question. Take a bureaucrat in Washington. Does the stuff he writes after 20 years better than it did when he started? Is experience any good? Does the use of a large number of different languages make a programmer any good? No. Experience, use of a bunch of languages, none of those seem to make a good programmer. That is not what does the trick. What does? What does make great writers? It is apparently the ability for the individual to set up a criteria of what they privately consider good programming and criticize themselves and hold themselves to a high standard of writing. Now, White, who wrote Strunk and White and was a writer for New Yorker, was a very good stylist. He points out how many times he failed to follow his own instructions. Good writing is like playing a good game of tennis. You know all the moves, but somehow or other you can't put them together right. Writing is a very hard business. It apparently is a matter of the individual doing it. Now, I spoke a top down and bottom up. I once had lunch with what were generally considered at that time 2 of the best programmers at Bell Labs. We were eating in a restaurant, and I asked them which they did. One guy said, well, he started and just sketched out the whole logical structure with putting these boxes. I was here, 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 and here, and got the whole structure going. Then he filled in the boxes in any order he felt like. The other guy said, well, he started someplace and so he expanded out. Now, to what extent they were pulling my leg, I don't know. But in fact, the two guys were rather different. One was a top-down programmer, one was a bottom-up programmer. I'm inclined to believe top-down is better, but the evidence is not that wonderfully good that I can say that flatly this is the best way to do it. The young lady I spoke of several times who worked for me, I tried to get her to top-down. She couldn't do it. She could run from bottom-up, but she was a superb programmer. But she started the inner loop and expanded on out. She couldn't start at the top and go down. So I don't know what makes good programmers. But I suggest to you strongly that experience is not so good, nor are teachers of programmers. While at Bell Labs, there was a guy named Kernahan who was a good stylist and also was a good writer. And I told him we need a book on programming. What we need are bad examples and good examples, just like you find in handbooks on English. Well, I needed a little for a while, nothing happened. I finally took a carton of programming books and took it over to his office and said, here's a bunch of books, you can look at those and see what's wrong. Every bad example which he used in his book came from a book on programming and held up as a good model. That tells you the professors who teach programming are not necessarily very good programmers. The textbooks would not support good programming. They were provided a large number of very, very hideous examples. One of the best one is a long program he copies down and says, well, that's a long program, must do something, let's go after it. And so he analyzes this and removes this, and this. He finally comes down to a program about 4 lines. That's all there is to the whole thing. Several other ones are absolutely spectacular at how bad they were and how they didn't do it. And his criteria was quite correct. If the program doesn't get the right answer, it doesn't matter anything else. And some of those wouldn't even get the right answer, what they're supposed to do. And they were in books on programming. So you see, we face a very, very difficult problem. I have compared software with writing. They're not exactly the same. But there is a great deal of element of this truth in it. Writing, particularly novel writing, is restricted by your imagination to a great extent. Programming has got a great deal of latitude. Now, what I did when I got myself involved in programming for a while, I deliberately adopted engineering restraints. For example, I had made mistakes in counting around when we had to simulate index registers. They weren't in the machines originally. I picked a fixed way of doing it. I always wrote them the same way. It had several merits. I didn't make mistakes, but also in scanning a program, that block I could recognize immediately because it was always the same way. Never a variation. I had a bunch of other very rigid ones. For example, the moment I read anything in, I printed it out. I was sick and tired of having programs whose answer I had, but I didn't know the problem because the parameters hadn't been read out. So every time I read a number, it immediately was printed out. I made several fixed rules like that, and I think I profited greatly by adopting some rigidity. Now, my choice in the loops was very bad. The choice I made, you couldn't do a loop no time. Now, a guy in numerical analysis doesn't want to do a loop no times. But a guy in artificial intelligence frequently wants not to do the loop. So I had picked a bad form. I wasn't necessarily perfect, but I found the adoption of rigid rules for myself was a great help because I could recognize patches of program later on. I tried to, what I told you, adopting internal standards of what a good program was, not good programming, and tried to hold myself to it. But what happened to me was an unfortunate thing. Just about the time Fortran was becoming reasonably available, my boss said to me one day, Hamming, you cannot compete with the people who are working for you. You cannot go on programming. I protested a little bit, thought about it, and I agreed he was right. I had not to program. I knew how to do it, but I couldn't practice because my boss was right. You should not compete with people working for you. It's not fair. When I came here, I no longer had programs working for me, so I got, the school at that time was issuing some nice little hand programmer calculators to students. and I was asked to teach a course on it, so I wrote a book on how to write programs in that language. And the book is a very nice one. Of course, it's long since out of date, but it was nice enough so my friend of mine the other day asked me, did I have any more copies of that manual, because he wanted to look at the style of which the manual was written. So I'm inclined to believe that I think it's right to say I know something about programming, that I know something about style. But style of a programmer is as variable as styles of writers. I do commend top-down, I do commend some other things like that, but I admit that there are other ways. You have to find one you like, but it's one thing to program as an individual. It's a very different problem when a group undertakes to do the job. Very, very different. A team of programmers is a very different problem than an individual writing programs. And I've had very little experience with that, but I can easily see that the group probably needs to get together and agree that they will accept certain restraints in their programming. But don't let those restraints be imposed unless you can write a program which will scan. Does this program obey those rules? If you can't write a program which checks that somebody else's program is obeying those rules, forget it, because you haven't got the manpower to check that everybody is following the rules. You have to have the machine check it. Those rules which are easily checkable on a machine are great, because when later on scanning something, if everybody is using the same step, that block there and that block there will be immediately identified what it is, and then they can orient themselves in the programming. If whimsically they're interchanged one instruction for another in a different order, same block but just interchanged, it's not so easily recognized. And in fact, if you interchange a block of code, you can change one instruction, you can cause chaos. You may remember there was a time sometime back when the telephone company was horror, brought down most of the East Coast for a while of telephoning. Remember that? All it was that there was a block of programming and somebody wanted to change a couple of those to speed things up. Well, it was such a small change that they agreed not to go through the 3-month routine testing of the program. It crashed the whole damn East Coast practically, right? It's not easy when you interchange even instructions of what will happen. And the telephone company, to its very great shame, slipped up once and did not follow its own rules about testing, because it was so obvious it must be the same. Well, I've told you software is a major problem. It will not go away. But it is a problem involving you as humans. The more I study and think about programming, the more I understand I'm looking at human beings. I preach to you, in summary, remember, write psychological rather than logically. Write so it can be followed. Write so that you 5 years later will know what you were doing. Don't do some cute trick. You won't remember. Don't take some advantage of some peculiar feature of a machine. On the 650, they asked me when did I want one delivered. I said, I'll take the 11th machine off the production line. I know the first couple have bugs, you'll fix them up. They won't be like other machines. I want to get one so that every other machine of that bunch, if the program runs on my machine, it'll run on that one. I also took the minimal machine with minimal attachments, so that whatever I did would run elsewhere. Getting special attachments on, if you put attachment A followed by B, or B followed by A, the machine will be wired quite differently inside. They may behave differently. You can't necessarily depend upon these things. So you want to be very careful when you get involved in machines. Now we're doing better, but I think you know about the Pentium chip. You've heard about that. We still can't do things right. So I leave it to you this very important problem. It's extremely expensive, and it's going to get more expensive. Humans are going to become more expensive. Machines are going to become cheaper. So the problem of programming is central. And we'll take up something next time. I'll take up applications, and we'll go on to AI, which really bears on this question of how people think and such other things. So we'll see you. I think there may be a shift in the room one of these days. If so, you'll be notified.